Okay, so our next thing to talk about is there's a relationship between the rank and the nullity. A few things I want to say about the rank in the meantime. The rank of A and the rank of A transpose are always going to be the same. The way that you can convince yourself that this is true is think about just kind of a generic matrix where you have um, maybe something like that. So here this matrix is in reduced row echelon form. There's no way to make it look any simpler. And if you were to take the transpose of this, what you would end up with would be a matrix that's not in reduced row echelon form anymore. Um, so let's write what this is: 1, 0, 1, 0, 2, 3, 0, 1, 4, 0. But what you could do is you could now think about doing row operations, and you could take, for example, this 1, 0, 0 in the first row and get rid of these. You could make those zeros. So you could do elementary row operations there. Likewise with this, you could turn those values there, 0. And then now that's in reduced row echelon form. But the point is that the number of pivots that you're going to start with are going to stay the same when you take the transpose, because you can use those pivots to get rid of the other values in that column. And so since the number of pivots is going to be unchanged by taking the transpose, that means that the rank of A and the rank of A transpose are equal. Okay, and so that tells you that there's some relationship between the row space and the column space, because if you think about um, that's why that's why the row rank and the column rank of a matrix are equal, is because you can do this transpose trick and you can turn rows into columns basically. I'm being slightly imprecise, but that's really the gist of the row rank and the column rank being equal. Another thing to say is that oftentimes we study this system of equations ax equals b, and ax equals b has a solution, it turns out, if and only if, so if and only if b is in the column space of A. Okay, that's a pretty self-evident fact once you think about it. Maybe this is not something that we would have thought of right away. Once I say it, hopefully it's obvious, because if you look at ax equals b and you think about what are what's the column space of A. So again, I think just an example will go a long way here. You have 1, 2, 3, 4. And if you look at what's the column space of A, well, that's going to be the span of the set of vectors of the, well, columns, 1, 3, 2, 4. And so that's going to be the set of vectors of the form, say, C1 times 1, 3 plus, let me use A and B here instead of C, plus B times 2, 4, where A and B are real. And so if you think about, and I shouldn't use B, bummer. Let me go back to C1 and C2, sorry. I forgot that B already stands for something in our problem, so I shouldn't use it twice. So anyway, so the span is the set, and if we want to have a solution, that means that AX equals B has to have a solution. In other words, B has to be in the column space of A, because the column space is the set of linear combinations here. So to say that AX is equal to B means that you can write B as a linear combination of the columns of A. 2, 4 equals B. So let's call B B1, B2. Okay, so that's a fact that hopefully when you sit down and think about it, that seems perfectly obvious. Again, even if we didn't think about it to begin with, now that we've thought about it, again, I want it to be supernatural. I want you to be able to just kind of feel like that is obviously true. Anyway, so that's something to say. So ax equals b has a solution if and only if b is in the column space of A. All right, and we're ready to get to the main event here. And this is going to be called the Rank-Nullity Theorem. So it turns out that there's a relationship between the rank and the nullity of a matrix. If A is an m by n matrix, so that n is the number of columns, that turns out to be the relevant term here. I don't really care about m at all. But if we have n columns, then it turns out that the rank of A plus the nullity of A, so the dimension of the row space or column space and the dimension of the null space, always add up to give you n. In our previous example, we had a 3 by 3 matrix where we saw that those added up to give us 3. The reason why it was 3 is that it was a 3 by 3 matrix, so we have 3 columns in particular. So we don't care what this first value is. We know that the rank and the nullity have to add up to give us n, the number of columns. So for example, there's a few different ways that we can do this, but let's look at an example of a matrix that's already in reduced row echelon form. So let's say we have something like 1, 0, 2, 3, 0, 1, 0, 1, 0, 0, 0, 0, and let's make it a 3 by 4 matrix. Let's think about what's the rank of A going to be. So the rank of A is going to be 2. And actually, let me do one more thing here, just to 4 is an even number, so you can, let me just add a column of zeros there. So the rank of A is going to be 2 because you have 2 pivots. Okay, so this is a 3 by 5 matrix now. So this rank is going to be 2 because you have 2 pivots. You have this one and this one. Okay, and those are your 2 pivots. The nullity of A, let's think about what that would be. The nullity of A, well, we'll figure out what that is in a second, but if we were to try and write down all of the solutions that we would get here, what we would end up with is we would look at these two equations, right? So think about this as x1 plus 2x3 plus 3x4 equals 0, and x2 plus x4 is equal to 0. x5 can be whatever we want. So x5 is free to be whatever term we want. Let's call it t. X4 is going to be one parameter. We can call that s. X3 is going to be another parameter. We can call that r. And then we can write x1 and x2 in terms of r, s, and t. And so x2 is going to be minus s. X1 is going to be minus 2r minus 3s. And so it turns out that our solution set, the null space in other words, but the solution set to ax equals 0 is going to look like this. We're going to look like x1, x2, x3, x4, x5. And that's going to be, we might as well just write it out. It's going to be negative 2r minus 3s, negative s, r, s, and t. And so that's going to be r times the vector 0, 0, 1, 0, 0, plus s times the vector negative 3, negative 1, 0, 1, 0, plus t times the vector 0, 0, 0, 0, 1. And I think I'm missing something for the r's. Yeah, the first entry in the r should have been a minus 2. Okay, but we're done, basically. In fact, I could have ended over here. The nullity is going to be 3 because the nullity refers to the number of parameters that we have, and we have 3. We have r, s, and t. So the nullity of A is going to be 3. And another way that we could have known that the nullity of A was going to be 3 is that I know that the rank and the nullity have to add up to the number of columns that we have for A, which is 5. So it's going to be 5 minus 2. So 5 minus 2. Okay, so that fact right there is the rank-nullity theorem. If you look at the rank of A and the nullity of A, those have to always add up to n, where n is the number of columns of a matrix A.